Hello, everyone. For the last lecture of the semester, we're going to continue what we started in the last class, talking about reaction kinetics, or the speeds of reaction. In particular, we're going to focus now on what your book refers to as integrated rate laws. You may remember that in the previous class, I introduced briefly this quantitative expression for a so-called reaction rate law, where the rate was dependent on the concentration in some way of the reactant A, in this case, as a function of time, where the dA dt is the rate of change of the concentration of A, the reactant, and that this was equal to some rate constant, which is a numerical constant with certain units that depend on the reaction order, and the reaction order N, which is a power of the concentration of A. So now in this class, what we're going to do is to develop this further by considering various values of N, the reaction order. And in particular, we're going to talk about 0, first, and second order reactions, where N is 0, 1, and 2. Now, for a zero order reaction, in essence, what it says is that the rate does not depend on the concentration of A, which may seem a little puzzling at first, but we'll talk about why that happens in a little bit. The differential expression then is that the rate is some rate constant, and in all of these cases, the subscript of K is simply the reaction order. And so in this case, it's K sub 0 for a zero order reaction. And the rate depends on the rate constant and some concentration of A to the 0 power. Well, anything to the 0 power, of course, is 1, which means that the rate does not depend on the concentration at all. It's simply equal to K sub 0. And that is then in turn equal to minus 1 over A dA dt, where this is the rate of change of the concentration of A. So the integrated expression, if we put the dt over on the left and put the concentration of dA as it is with just dA and integrate it, we get the integral of the concentration of A is simply of dA is simply A, and that equals then minus AK0 times T, the integral of dt is just T, plus the constant of integration, which is the initial concentration of A. So what we're going to do in all three of these cases, for zero, first, and second order reactions, is we're going to come up with some plot, some simple arithmetic plot that can be made to demonstrate conformity to that type of kinetics, zero, first, or second order. In this case, if you look at this integrated expression now, we could plot simply the concentration of A versus time, and it should yield a straight line with a slope of minus AK0 and an intercept of the initial concentration of A. So here's an example of a zero order reaction. 2 N2Os going to 2 N2s plus O2. Now this reaction occurs over a platinum catalyst, but in the absence of the platinum catalyst, it will not occur. The reaction is too slow to observe. But over a properly prepared platinum catalyst, the reaction will proceed to give 2 N2s and an O2. So what's actually happening then is what's shown in this picture down here. The molecules of N2O, which are in the gas phase, all right, will collide with the platinum surface periodically and adsorb on it. There are some forces that result in N2O molecules being adsorbed, as it were, on the platinum surface. And the reaction to yield 2N2 and O2 occurs only on the platinum surface. It does not occur up in the gas phase itself. So the only concentrations of reactants that matter for this reaction are the ones that are on the surface of the platinum. Well, if the platinum surface is already completely filled with N2O molecules that have been absorbed, it won't make any difference to the reaction rate, the observed rate, if the pressure or concentration of N2Os in the gas phase is increased, because the surface concentration is already completely filled, and increasing the concentration or pressure in the gas phase doesn't change any further the concentration on the platinum surface. So as a result, the rate of the reaction, which occurs on the platinum surface for N2O molecules to decompose into 2 N2 molecules and an O2, depend only on this the coverage of the platinum surface. And so for that reason, because it's not dependent on what you can observe, which is the pressure in the gas phase, the reaction looks as if it's independent of the concentration or the pressure of the N2O, which is exactly what's observed. So the kind of behavior for this, a reaction like this, is zero order, and you'd find that if you plot the concentration of A versus time, you will get a straight line that does not depend on the initial concentration. It simply means that as the reaction proceeds, as T gets larger, A simply gets smaller. Concentration goes down linearly with the reaction time. Now, for a first order reaction, which is much more common, and in fact, among all the three that we're considering, it's by far the commonest reaction order, our first order reactions. In this case, the rate is dependent on the first power of the concentration. In other words, simply directly on the concentration. And this makes sense if you think about how the reaction is occurring, either in the gas phase where the molecules are colliding with each other during the course of time, or in a solution, in some solution reaction. The molecules or whatever, or ions or whatever in solution are colliding with each other. And the larger the concentration or pressure of A, the more collisions per unit time there will be. And therefore, the reaction rate will simply depend on that concentration to the first power, which is what's observed in first order reactions. So here's the differential expression for a first order reaction. The rate, again, is 1 over A times the time derivative of the concentration of A. In other words, the differential rate of change of the concentration of A with time, and that's equal to minus K1 times A. Now this minus sign here could be either over on the left or on the right. It makes no difference. But it's a minus sign because the concentration is going down with time. So if we integrate that by separating the variables again, put the dt over on the right and the A over on the right, put the concentration of A on the left under the dA, we've now separated the variables. We have A on the left, T on the right. So the integration is very simple. The integration of dA over A is simply the log of A, as we know from elementary calculus. And the integral of dt is simply T, which is shown here. So the integrated expression then is simply the log of A, concentration of A, equals minus AK1. Now we have a first order rate constant, so it's shown as K1, times the time, plus the constant of integration, which is the log of the initial concentration again. So again, looking for a plot that will confirm first order kinetics by plotting data that are obtained experimentally, we could plot the log of the concentration of A, which has to be experimentally measured as a function of time, the log of the concentration of A versus time. We should get a straight line with a slope of minus AK1 and an intercept of the log of the initial concentration, which is, as we said, right here. An example of a first order reaction, and there are many, many of these reactions that obey first order kinetics, is the decomposition of N2O5. N2O5 will decompose to 2 NO2s and 1/2 O2. And if you make a plot of these data, this is what you'll observe. Now, first of all, this is a plot not of the plot that we were talking about right here. This is a plot first that shows the dependence of the reaction rate here on the initial concentration of N2O5, which, as we would expect, if the initial concentration of the reactant, N2O5 in this case, increases, so also should the initial rate. And that's exactly what's shown by this plot. As the concentration, and these are all, the data points are not shown on here, but there's a series of different experiments here that involve different initial concentrations and then measure the initial rate. And what was observed is that the reaction follows a plot that looks linear. In other words, if we double the initial concentration, we double the initial rate. If we triple the initial concentration, we triple the initial rate. And that's all that we're observing here. So that the rate is dn, the rate of change of N2O5 with respect to time is just minus K times the concentration of N2O5 for the initial concentration. Now, if we make the plot that we just talked about before, by plotting the log of the N2O5 concentration versus time, we indeed see a straight line which has the slope of minus k, which is minus 1.72 times 10 to the minus 5 reciprocal seconds. And so that means that k is 1.72 times 10 to the minus 5 reciprocal seconds. This is the plotted expression, the log of N2O5 versus T, and the intercept is the initial concentration of N2O5 for this particular experiment. This is for one experiment that starts with some initial concentration. Now, one of the characteristics that we'll see for rate constant units is that the rate constant will have units that always involve reciprocal time and possibly some inverse concentration units. What makes first order reactions unique is that the rate constant involves only reciprocal time, either reciprocal seconds or minutes or hours or whatever time unit was used to measure the rate of the reaction. We'll see some examples of that as we go on. Now, what about second order reactions? Well, in this case, where the second order means that the rate depends on the square of the concentration of the reactant A. The differential expression looks like this, where everything is the same as before, except now the concentration of A, or pressure if it's a gas, is raised to the second power. So now, again, separating variables, putting the A squared concentration under the dA, putting the dt on the right, as well as the coefficient A on the right, and integrating. The integral of dA over A squared from elementary calculus is 1 over A, as you know. The integral again of dt is simply t. And so the integrated expression looks like this. It's 1 over the concentration of A equals AK2, the rate constant for the second order reaction, times T, plus the constant of integration, which is 1 over the initial concentration. This little 1 here should be an I, by the way, a misprint. So again, looking for an equation that we can plot to demonstrate conformity to second order kinetics, we could plot a plot of 1 over A, which is A to the minus 1, versus T. And if the reaction conforms to second order kinetics, we should see a straight line with a slope of AK2 and an intercept of 1 over the initial concentration. An example of that is shown here. Put this back up. The reaction is 2 NO2s decomposing to give 2 NOs and an O2. So if we plot one for a series of experiments, and again, the data points aren't shown, but this is a series of several experiments that each use different, this is a plot of one particular experiment that used a particular initial concentration, in this case 100 moles per liter. And the plot that's shown here is one of 1 over A, 1 over the NO2 concentration, versus time. And we indeed get a straight line with a slope, in this case, that's 2K, because it has this little A value here is now 2 for this particular reaction. So the rate constant would be the slope divided by 2. And it demonstrates that the reaction shown here conforms to second order kinetics. Here's an example of what are the same set of data that were obtained by measuring the reaction for a period of time and measuring the concentration of the reactant versus time. And it's plotted by two different means. The reaction is this. It's C2F4, that's tetrafluoroethylene, dimerizing to C4H8. This is occurring at 450 K, okay? Now, the data points here are the experimental data points, and they're the same in both experiments. They look different here because they're plotted differently, but the data points are exactly the same. In this case, in the left-hand case, they were plotted by looking at the first order rate expression for a reaction that would follow first order kinetics. In other words, it plots the log of the C2F4 concentration versus time. As you can see, the data points don't follow a straight line very well at all. In fact, they're curved looking if I plot it in this fashion, the log versus time. But if I plot those same data as 1 over the concentration of C2F4 versus time, now I get a straight line where all the data points fall on the straight line. And this straight line, again, just like the one we looked at before, will have a slope that's equal to 2k, because the coefficient here is a 2. And so the rate constant would be the slope divided by 2. And this is an example of how rate data that are obtained in separate experiments can be tested to see what kind of reaction order they conform to. Either first order, which this one does not, or second order, which this one does. Similarly, if we had taken a reaction that follows true first order kinetics and plotted it according to this, the points would fall on the straight line. But if we plotted the second order version, 1 over, it would be curved. It would look like this. So here's a summary of what we've just been talking about for these various reaction orders and what we observed. There are several things that are listed here that are observed for different reaction orders of 0, first, and second order. As we saw, the rate law for a 0 order reaction is simply the rate equals k. It doesn't depend on the concentration at all. Don't confuse that with the concentration of A as a function of time. Of course, the concentration will decrease with time, and it will do it linearly, because as the reaction proceeds, the concentration of A will keep getting lower and lower. But the rate that you observe does not depend on that concentration. It simply is a value, a fixed value, that is the rate constant. For a first order reaction, as we've seen, the rate is some rate constant times the concentration to the first power. In other words, the rate depends on what the concentration is. If I double the concentration of A, the reaction rate will be twice as fast. If I cut it in half, it will be half as fast. For a second order reaction, as we've seen, the rate depends on the inverse of 1 over A squared, so times the rate constant. So now the data points would follow a straight line if they obey second order kinetics. So the integrated rate laws are shown here for all 3 cases. As we saw, the rate constant, the concentration of A is simply minus KT plus the initial concentration, which will always be a simple straight line, because the reaction rate depends only on the rate constant itself. For a first order reaction, the log of the concentration of A versus time will give a straight line if it's plotted versus time. So the log of A equals minus KT plus the log of the initial concentration, which is the intercept. And for a second order reaction, a plot of 1 over A versus T will give a straight line with a slope of K and an intercept of 1 over the initial concentration. So these are the things we just talked about. Those are the plots that are needed to give a straight line. And from each of these 3, which I wrote in here in green, the rate constant for each of the 3 cases can be shown simply by looking back at those integrated rate laws. The rate constant for a 0 order reaction is simply the concentration of A divided by time, which will be a constant, because as the time goes up, the concentration goes down. For a first order reaction, the rate constant is simply 1 over the time. And for a second order reaction, the rate constant is 1 over the concentration times time. You'll notice that for the 3 different reaction orders, only the first order rate constant does not depend on concentration, because if you double the concentration, you double the reaction rate. If you cut it in half, the reaction rate gets cut in half. And so the rate constant, though, is a constant, and it depends only on the time of the reaction. So here's that relationship we talked about, the relationship of the rate constant to the slope of the straight line. For a 0 order reaction, the slope is minus K, the same as it is for a first order reaction. And for a second order reaction, it's simply K itself. So here's a little comparison that shows arbitrary plots for first, second, and 0 order reactions. And what is plotted is the concentration of the reactant divided by the initial concentration, which is a constant. So this, you can just view this as the concentration itself, starting at whatever the initial concentration was as 1. And of course, as time goes on, the reaction the concentration of whatever the reactant is will decrease. So for a zero order reaction, what you see is a straight line, because as we said, the reaction rate does not depend on the concentration, but of course, the amount of reactant remaining does depend on the time. And so it simply goes down linearly with increasing time. First and second order reactions give curved lines like this. And we'll see some more examples of that in a minute. First order reactions and second order at low times are almost close to linear, but they're not, they're curved lines. But as the reaction time gets longer, you can see that the second order reactions curve more than the first order reactions do. And that's because the reaction depends on the square, 1 over the square of the concentration of the reactant. Here's something that shows these plots for 2 different cases. The ones on the left are both for first order reactions. The ones on the right are both for second order reactions. And what you see for simply the concentration, and again, this is divided by the initial concentration, so you can simply look at it as the concentration itself. The concentration as a function of time, of course, the concentration goes down with increasing time, as we expect. What's shown here for these 4 numbers, 0.2, 0.1, 0.05, and 0.025, those are the rate constants in reciprocal seconds. You can see that the higher the rate constant is, the faster the concentration decreases with time, as you would expect. For example, for the rate constant of 0.2, the decrease in concentration with time is much faster than it is for a rate constant of only about 1/8 that much. And so the other ones fall in between. But the general behavior is just what we saw on that preceding slide. For a second order reaction, the same general behavior is observed as for a first order, with increasing rate constant. The reactant decreases with time, and the higher the rate constant, the more rapidly it decreases with time. But as you can see, the curvature of the second order reaction for equal rate constants, say 0.025 versus 0.025 here, the curvature is greater for the second order reaction than it is for the first order. The bottom curves, in both cases, are the plots that we've just been talking about for first order and second order. The plot for the first order is the log of the concentration of A versus time. And the plot for the second order is 1 over the concentration versus time. And in both cases, we see straight lines. And again, these are the different rate constants. 0.025, 0.05, it's hard to see, it's a yellow line here, 0.1 and 0.2. And so with increasing rate constant, the decrease of log A with time is more severe than it is for lower rate constants. And the same thing is observed for second order reactions, where in this case, the slope, of course, is positive rather than negative, as it is for a first order reaction. But again, the same thing is true. With increasing time, the higher the rate constant, the faster the reaction proceeds. For a rate constant of 0.2, the rate goes up, or the reaction rate increases fast. The rate goes faster than it does for a rate constant of 0.1 or 0.05. And so this simply compares the overall behavior of first order versus second order reactions. Now, one of the characteristic features of reactions that can be measured is what's called their half-life. The half-life simply refers to how long does it take for the initial concentration to be decreased to half its initial value, okay? And that's what a half-life means. We can derive these fairly simply for the 3 orders that we talked about, 0, first, and second order, by simply taking the integrated expression. Here's the one for the 0 order reaction. And if we now say at T sub 1/2, then the concentration of A will be half the initial concentration. So that's expressed here. And so if we now rearrange this, put in for A 1/2 of A sub I over here, and rearrange it and solve for the half-life, the time now is T sub 1/2, we get that the half-life is the initial concentration divided by 2 times the rate constant times A, whatever the coefficient A may be. For a first order reaction, we do the same thing. Here's the integrated rate expression. As we've seen before, the log of A is equal to minus AK1 times T plus the log of the initial concentration. So at the half-life, then, the concentration of A has decreased to half its initial value. So A now, at the half-life, is A sub I, the initial concentration, divided by 2. So if we put that value in for the log of A, rearrange it, you'll find that the half-life is simply the log of 2, the natural log of 2 over AK1. The natural log of 2 is about 0.693, so that's where this number comes from here. And for a second order reaction, here, again, here's the integrated rate expression, and at the half-life, the concentration of A has decreased to 1/2 the initial concentration. So putting that value in for A, again, here, and rearranging, you find that the half-life is 1 over K2 times the initial concentration. Now, all three of these expressions here for the zero order, first order, and second order will give the time it takes for the initial concentration to be decreased by half. But there's an important difference between the three expressions for the half-lives. You'll notice that the half-life expression for a zero order reaction and a second order involve the initial concentration. For a zero order reaction, the initial concentration appears in the numerator for the half-life, and for a second order reaction, it appears in the denominator. But a first order reaction, the initial concentration does not enter into the half-life expression. That's a very important point because it makes the half-life of a first order reaction a very useful number to have. Whereas for a zero and second order reaction, the half-lives are less useful, less meaningful, because they depend in one way or another on the initial concentration. But for a first order reaction, the half-life does not depend on the initial concentration. And the reason for that, of course, is because if the initial concentration is twice as high in the second experiment compared to the first, then the reaction will go twice as fast. And the half-life is reached in the same length of time. So it's for that reason that the half-life of a first order reaction is particularly useful. It's a way of measuring the rates of first order reactions independently of individual experiment measurements. What happens is this. Here's that first order reaction we looked at before. This is N2O5 decomposing. The initial concentration is 0.1 in this case. And it turns out that by experimental measurement, we can show that the time it takes for the initial concentration to decrease by half from 0.1 to 0.05 is 100 seconds. So this is one half-life, as it's called. After 200 seconds, the concentration of 0.05 has decreased another half to 0.025. For another 100 seconds, which is now 3 half-lives, it's decreased to 0.0125, which is 3 half-lives. But the time it takes for it to do this does not depend on the initial concentration. If this initial concentration had been 0.2 instead of 0.1, the time it would take for it to decrease by half would be from 0.2 to 0.1, but that would still be 100 seconds because the rate would simply be twice as fast because it's a first order reaction. And so what you can see here, I don't know if you can make this out, the half-life, which we just saw is the log of 2 over the rate constant, is 100 seconds. Based on that experimental measurement, that the half-life is 100 seconds, and you can do that by simply measuring the concentration as time increases until you get to a value of 0.05, and then noting what time that took to do, in this case, 100 seconds. If you just rearrange this, the rate constant then is simply the log of 2 over 100, which is 6.9 times 10 to the minus 3. So the rate constant of a first order reaction can be determined easily by measuring the half-life. That's not possible for a zero or second order reaction because they depend on the initial concentration. So the half-life is not uniquely useful. Here's another example of a first order reaction. As you may know, radioactive decays all follow first order kinetics. And the reason they do is because if the amount of the radioactive isotope is doubled, the rate of decomposition will be twice as high because there's twice as many isotopes there to decompose. It's for that reason that the half-life of a radioactive decay is a particularly useful number, because it doesn't depend on the initial amount of material that's decomposing or decaying radioactively. The one that's shown here is for strontium-90 going to yttrium-90. Now, you may not have had any experience yet with radioactive decay, but this terminology here, this nomenclature, is that the numerator, the upper number is the atomic weight, and the bottom number is the atomic number. For strontium, the atomic number is 38, and this happens to be one of the isotopes of strontium. It's strontium-90. It decomposes to give off an electron, which is called a beta particle, and because the atomic number now is one greater, it's now 39, that makes it a different element. It is now yttrium. The atomic weight stays the same because the electron has essentially no atomic weight compared to protons and neutrons. Well, for this particular decomposition, starting with this arbitrary number of 10 grams of an initial amount, in order for it to decrease its amount to 0.25 grams, it takes 28.8 years. Now, that may seem long compared to some of the other reaction rates we've talked about, but you can see that after one half-life, the amount has gone down to 5 grams. After 2 half-lives, it's down to 2.5 grams. After 3 half-lives, it's down to 1 3/4 grams, and so on. And so, but the time it takes for strontium, in this case, which is a radioactive isotope, to decay is a long time. It takes almost 30 years. That means if strontium is present in anything that we eat, and the radioactive isotope is present, it could be a problem. And the reason that this is pointed out is because strontium occurs in nature with calcium. They're both in the periodic table group 2, and strontium falls just below calcium in the periodic table. And they often occur together in nature. In fact, most of the time they occur together in nature. Calcium is much more abundant than strontium, but there's always some strontium present with the calcium. So if by chance some of the strontium happens to be radioactive, when calcium is ingested, which it is when you drink milk or other calcium-containing foods, you could be ingesting some radioactive strontium. Doesn't happen very often, but it's possible. And it's one of the reasons why this particular decay was studied at great length to determine its half-life. The half-life is not very promising. If you were to ingest some strontium-90, it would take almost 30 years for half of it to go away. And in fact, for all of it to go away, or at least for 4 half-lives, it would take longer than a human lifetime. So that's the reason why this particular decay was studied at great length. And steps were taken to try to eliminate the presence of strontium in the calcium that occurs in the food that we eat. So the last thing we're going to talk about in this context of rate expressions are multi-reactant reactions. Now, what we've talked about so far have been reactions in which there's only one reactant. We talked about N2O5 decomposition, we talked about NO2 decomposition, and so on. But for reactions, which are many, of course, that involve more than one reactant, A, B, C, and so on, the kinetics can be measured as well, but each of the individual reactants has to be separately taken into account. For reactions that have more than one reactant, each of the individual reactants will have its own reaction order. So a reaction can be first order in A, N in B, and something else in C. And that's what we're going to talk about now. So that if we have a pseudo-general reaction like AA plus BB plus CC going to products, the reaction rate then, just and by analogy to the ones we talked about previously for single reactant reactions, the rate will be minus 1 over A dA dt, which is equal to 1 over B dB dt, which is equal to 1 over C dC dt. The reason that all of these are the same expression is because they're all reacting, presumably, at the same time. There's some A, some B, and some C, depending on what these coefficients are. And so the reaction rate can be written as any one of the three, and that has to be equal to the rate constant, whatever that may be, times the concentration of A to a power, X in this case, times the concentration of B to a power, Y in this case, times the concentration of C to the power Z. And so X, Y, and Z are the reaction orders in the reactants A, B, and C, respectively. And the overall reaction order is simply the sum of all three reaction orders. So for a set of reaction data like this, I'll just show this as an example. For the following reaction, the experimental data in this table were collected. All right, this is a reaction, as you now recognize very well, as a redox reaction. Bromate plus 5 bromides plus hydronium ions are going to 3 bromines and water. What you can see here is that the bromines in the bromate ion are being reduced from an oxidation number of +5 to an oxidation number of 0, and the bromines in the bromide ions are being oxidized from an oxidation state of -1 to an oxidation state of 0. That's not necessarily relevant to what we're talking about now, but you should recognize this as a redox reaction that we just finished talking about in the last few lectures. So there are 4 experiments that were done, and this is how these things are always accomplished. You have to carry out individual experiment in which one, in this case, there are 3 reactants, in which 2 of the 3 reactants, their concentrations initially stay the same, and only the third one is varied, so that you can determine what the reaction order is in just that one that's being varied. And that's what these data in this table show. So in the first experiment, which is usually referred to as the control experiment, that everything else will be compared to. In this particular case, each of the 3 concentrations, the bromate, bromide, and the hydronium ion concentration were all 0.1 molar, all right? And the initial rate that was observed for that experiment was 1.2 millimoles of bromate per liter per second, okay? You can choose to express the initial rate in terms of any one of the 3 reactants you like. In this case, we're doing it in terms of the bromate. 1.2 millimoles per liter per second. All right. The second experiment involves keeping the bromide and hydronium ion concentrations the same as in the first control experiment, but doubling the initial concentration of bromate. And when you do that and measure the reaction rate, you find that it almost exactly doubles from the first experiment. That tells you immediately that the reaction is first order in bromate, because if the concentration is doubled, the reaction rate doubles, just like first order reactions do. In the third experiment, which again will be compared to the first, the bromate and the hydronium ion concentrations are kept the same as in the first experiment, 0.1, but the bromide concentration is tripled. And you can see in this case, the reaction rate in terms of millimoles of bromate per liter per second has just about tripled from the first experiment, from 1.2 to 3.5. That's very close to tripling. And finally, in the fourth experiment, once you've done experiments in 2 of the 3 components, as we did in experiments 2 and 3, you could now vary 2 components at the same time, because you already know what one of them will do from one of the previous experiments. And that's what this fourth experiment is doing here. The initial concentration of bromide is now kept the same as it was in the first experiment again, but both the bromate and the hydronium ion are being varied. The bromate is double, and the hydronium ion concentration has gone up by a factor of 1.5 initial concentrations. But we already know what the bromate will do when it's doubled. It doubles the reaction rate. So it went from 1.2 to 2.4. So we already know what that effect will be. So what's the additional effect, if any, caused by the hydronium ion concentration? Well, the hydronium ion concentration caused the reaction rate to go up to 5.5. Now, what does that mean? Well, the initial rate based on the doubling of the bromate concentration should be 2.4. But when the reaction rate went up to 5.5, what we can say is that the dependence on the hydronium ion concentration must be a squared dependence, because the 1.15 squared is 0.0225. And so putting that on top of the 2.4, that will give you the 5.5. So now these 4 experiments have given us information about the reaction order in each of the 3 reactants. So the rate law that's consistent with these data is the rate is some rate constant times the bromate concentration to the first power times the bromide to the first power times the hydronium ion concentration to the second power. So we would describe this as saying that the reaction is first order in both bromate and bromide, and second order in hydronium ion concentration and fourth order overall, sum of the three orders. Now, the overall fourth order rate constant can be calculated. We've got some of the data here from all four experiments. We can pick any one of the four. Now that we know what the reaction orders are, 1, 1, and 2, we can pick any one of these four experiments and put in the concentrations that we know for the three reactants, and from that we can calculate K. So the reaction, we look back up here, the rate constant K will be the rate divided by the product of all of these concentrations to their appropriate powers. Put all three of these below the rate and in the denominator. And what you'll observe then is the K is the rate observed divided by the bromate concentration to the first power, bromide to the first power, and hydronium to the second power. And if you do that, we'll pick out any experiment. In this case, I picked out the fourth one, where the initial rate is 5.5 millimoles of bromate per liter per second, right? And that's the rate. Here are the three concentrations that gave that rate, 0.2, 0.1, and 0.15. So simply dividing this through, you'll find that the rate constant is 12 liters cubed per moles cubed per second. And the fact that the units of the concentration have liters cubed per moles cubed, all right, is a reflection of the fact that there are three components here, and all of them are on a per second basis. So that's the reason why the concentration or the rate constant involves the units of what look like moles cubed per liters cubed reciprocal, and the reciprocal time, which, as I said, will always occur in all reactions. The rate constant will have units that involve reciprocal time in some way. So that concludes our discussion of these different reaction expressions for 0, first, and second order reactions.